Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on thin layer chromatography. So following on to the last video that I done, this is just going to be a video of me kind of going on to one type of chromatography that you should be able to, that you should know. It's very similar to the one that you've done at GCSE, but it's not exactly the same in terms of the method is the same, and the method is the same, but it's the equipment that's being used is slightly different. So the stationary and the mobile phase are a bit different, but in terms of your understanding in GCSE of putting, dotting a compound on your starting line, allowing it to rise to the stationary phase, it's the same principle as that, but our stationary phase and our mobile phase is slightly different. And there's a couple of other things that you should be aware of when going through this topic. So, thin layer chromatography, or TLC, is a type of chromatography used to identify and separate chemicals in a mixture. So the setup, setting up the apparatus, right? So at GCSE, you know it as like thin filter paper, but we use something called a TLC plate, which is we use an aluminium TLC plate coated in silica or alumina. And substances to be separated or identified must be dissolved in an organic solvent, not inorganic solvent, and dotted along the bottom of the TLC plate. The TLC plate is placed in a closed jar with a small amount of organic solvent inside. I don't want to say a closed jar, I would like to say a beaker instead. But more importantly, this beaker, I mean, it could be a jar. I mean, but we're being so. But we have to be scientific here. We're using a beaker, right? So this closed beaker will be closed off by you can use an evaporating dish to close it off. But in general, that beaker is acting as what we call a chromatography chamber. So if you ever hear the word chromatography chamber, it's just a beaker with an evaporating dish on it, and that's just it's just a place inside that chamber is where chromatography is happening. But it's just imagine your TLC plate or your stationary phase where where chromatography is taking place is inside of a beaker with evaporating dish on it, and we call the beaker with the evaporating dish on it, we call that a chromatography chamber. So if you ever hear that, don't get really confused and say, oh, I've never heard that before. It is exactly what you've learnt. Is exactly what you understand. It's just called a chromatography chamber. Right, so to actually run, and also it has to be done in a organic solvent. There's many different types of solvents, but that is one key thing. And also depending on the solvent that you use will determine your chromatography. So you can have the exact same, you can test the exact same sample, but if you're dissolving it in a different type of organic solvent, you'll get different results. So your organic solvent matters, and it's a small amount. You don't need to have like a crazy excess, just enough that it touches the base of the TLC plate, so that it can allow for capillaration really. And a capillaration is just allowing the mobile phase to move up the stationary phase. Now to actually run the experiment, right? So again, I don't know why it said the jar. I use the word chromatography chamber. Or you could say beaker. You don't have to say chromatography chamber if you don't feel comfortable saying that. Chromatography chamber is more fancy way of saying it, but you can just get away with saying beaker. You can just say beaker, and I'd advise saying beaker, but if you say chromatography chamber, that's not a problem either. So the chromatography chamber is left, and the organic solvent in the beaker rises up the TLC plate and over the dots. The TLC plate is removed when the solvent front, which is the top of the rising solvent, on a plate near the top edge of the plate. And we can now use this TLC plate to either identify or separate the components in a mixture. So just how you understand it from GCSE, we leave our TLC plate, or you guys understand it as filter paper when you do it in GCSE, but I haven't shown. I mean, I'll show you a video of what chromatography of a what TLC plate feels like. It feels like this kind of plastic, kind of or metal, weird kind of sheet, plastic, hard. Think of like a cardboard piece of paper. It feels kind of like a bit like a cardboard piece of paper, but obviously we know it is not. It's aluminium. It feels like it's kind of same weighting as it, but it's imagine having like an aluminium plate that's coated in aluminium or silica, Silica, I believe, is just silicon dioxide, and aluminium means aluminium dioxide. I believe so. But it's coated. That's what the TLC plate is coated in. One side is shiny, and the other side is kind of like a white shape. And the white side is where you're gonna actually do your where you're gonna have your line, and you're gonna see the chromatography take place. I'll show you a better example later on. But the you just leave your once you've added your solvent into your beaker and you've drawn your starter line, and your TLC plate is just touching the bottom, just touching the solvent. You then add your evaporating dish, or you could add a you can suspend it, and you can do your reaction in a um, fume cupboard. You could do that as well. I'll go in a bit more detail about that later. But you leave it over a certain period of time, and chromatography will just take place, and your organic solvent will or your mobile phase, I should call it, will move up the chromatography paper by capillarization, and it will drag up specific compounds with it, depending on different depending on different properties of the compounds in that mixture. And then as you understand from GCSE, it will be brought up to different levels, and your solvent head will reach a certain point, which is just your solvent front. Your solvent head is where your solvent stops rising, and we can work out the RF values that you should know about at least. You should know about. So you should first of all, you have to measure how far your solvent head's gone from the starting line, and then you have to measure how far your individual spots or lines have gone from the starting line, and then you can measure an RF value. So I have an example here. I've done this I spent a lot of time making this kind of like diagram here. Maybe it went a bit over the top. I made this beaker extremely massively large for some reason. I don't know why. I was meant to just be a close-up on the beaker and then having a fume cupboard in the background with the clipper. So I'm gonna just highlight this here. So obviously, this is your support stand with your crocodile clip and your sidearm. Well, you have your support stand here. This is if you want to suspend it. This is if you want to suspend your chromatography paper, and I think that's a better way of doing it. It's better to do it this way because bits of if your organic solvent starts to evaporate, it can start to bind to the walls of the chamber, and then if your TLC plate is just put inside and it's just left to kind of stand against the walls of the container, some of the organic solvent can start to it could evaporate and then just condense somewhere randomly on your TLC plate, which you don't want because it could affect your results if you do like that. So I personally prefer to get it suspended, but always check with your teacher, ask them which way is better. But I don't really see much problem with it being suspended. So crocodile clip here is just to help suspend it up. A support stand, sidearm, obviously that's connected to the crocodile clip. That's connected to the TLC plate. I'll call this a TLC plate here. This would be our expected solvent front. It won't be. Again, I just want to make it clear. Your solvent front, which is how far your solvent has gone up your stationary phase. Kind of go through a little bit. Ooh. Sorry, I said that wrong. Yeah, our solvent front, which is how far our mobile phase has gone up the stationary phase. It's not going to be an exact straight line. It's going to be kind of a little bit wiggly, but you're kind of looking at the lowest point, and you're measuring it from that lowest point. Because that's how far it's gone, really. That's how far it's gone. Now, if it's really wonky, then you may have to do your experiment again. But if it's gone like half here, then you go from the lowest point. That's how far it's really gone. So, can I get this here? Can I get this? All of this here is your how far. I can't go through here. I'm not going to spend in much detail kind of scribbling it in here, but you get the point. Everything up until here is how far this is our organic solvent here, and that's how far it's gone up. The solvent head's how far your solvent has gone up your TLC plate. So we have our start line here. Oh, I'll use a different color. And then that the direction of the solvent. Sorry, have it written here. This is just our direction of the movement of the solvent. It's going to go upwards. So we'll have our chosen solvent, chosen organic solvent will be here. Is that clear? I think that's clear. Chosen organic solvent. And that's our expected solvent front. I can't have done that line way too big. I'm just trying to highlight everything because it may ask you to draw and label a diagram and just making sure that you get every single point here. I know everyone knows what's going on here. I'm well aware that everyone is aware of what this is, but in case they ask you to draw and label it, just being able to show direction of solvent movement isn't necessary, but the organic solvent, the solvent head, the starting line, and even the way that if they have asked you to draw it, showing that it's just lightly touching it, doesn't have to go all the way in. I may have done it a little bit too much here, but it should probably just about touch. But showing that your starting line is a certain level above. Obviously, you're making sure make sure your starting line doesn't touch the organic solvent. If you know why, because it could just it just means that your compound will just dissolve straight into the mobile phase here and won't move up the stationary phase. Will just dissolve straight into the solution here. So you want your mobile phase to move into your compounds and let it move up with the solvent up. Let it move up in the mobile phase as it goes up the stationary phase. Obviously has to happen a little measurement here. You would take that into consideration as well. I believe that's it. Yes. Now, also, I remember why I did this, and I said I remember I did mention to do something. I was like, I didn't just draw this for no reason. In the background, I have drawn a fume cupboard. The fume cupboard is there specifically for the fact that your organic solvent might be toxic. It might be very toxic. So you might need to do this reaction in a fume cupboard. So usually it's not, but there are examples where you may have a toxic organic solvent, and that's why you may want to do it inside a fume cupboard. It might be safer to do that, and you might want to mention that if they ever ask for safety precautions or anything taken like that, wearing goggles. Obviously, wear goggles. Keep your head back away from the organic solvent if it is toxic, but doing it in a fume cupboard is one way you can just make sure that you're doing it safely. One of the safety precautions you can take. The reasons why it does that is because obviously fume cupboards obviously is separated out from the rest of the environment out, and you have a massive hose here that takes out any organic compounds out. So that's just one thing that you don't need to mention this way, but I was just explaining why using a fume cupboard would be useful. But I just thought that would be useful. Now the third thing to do in terms of doing the experiment is now you evaluate your results. So eventually now your organic solvents will now move up the mobile phase and stop at some point in the stationary phase. So it moves up the stationary phase alongside the mobile phase, I should say. Is that the best way of saying it? Well, at least that the compound has the compounds here or the different compounds within the mixtures of these samples here have different affinities to the mobile and stationary phase. They're moving up the stationary phase due to the mobile phase, or they're moving up the stationary phase with the mobile phase. If that makes sense. Hopefully it makes sense. It starts here. Just as you're understanding GCC, this solvent head won't just be here. Obviously, it's going to move up. So if you liquid, you have your organic salt, your mobile phase here. It moves up the stationary phase, and as it moves up the stationary phase, then you'll start getting your streaks of you'll start getting your little streaks. It won't be a single dot. It'll be more like a streak. I've got a better example as showing you it below, but this is just more to do with understanding the setup before actually it rises up. Eventually, it will rise up to get this, and you'll get results, but just here is just showing you what's in the setup. And now we evaluate the results, right? So the mobile phase is the organic solvent, which is typically apolar, and its stationary phase is the TLC plate, which is typically polar. So the more polar substances will interact more. So like I said in the last video, the more polar substances will interact more with the stationary phase, and so will be found lower down the plate. And the less polar substances will interact more with the mobile phase, and so will rise with the solvent, the mobile phase, more quickly, and we find higher up the plate. Solvent, mobile phase, we know here is the same thing in this case here, but I like using the words mobile phase, stationary phase, and what was the other one? Mobile phase, stationary phase, and what's another word I was gonna say? Affinity. As the words mentioning, that's it. Mobile phase, stationary phase, and affinity are like a really good thing to mention with chromatography, because it's showing to the examiner, you know, that those that's specifically only for chromatography. Now you won't get marked down. They do allow other examples in the mark scheme, but just it's really promising to examiner, saying that you're using words like it hasn't moved up the stage phase that much, which means that it's a polar compound, showing that as a higher. So it hasn't moved up the stage phase that much, showing that it's a polar compound, meaning that the compound has a higher affinity for the stationary phase than it does with the mobile phase. And then you can go and say blah blah blah, so on and so on. But yeah, that's what I try to emphasize, using the words like affinity, mobile phase, and stationary phase, because that's the only time you can really use those words. But any other examples saying attraction and solvent or the TLC plate aren't wrong. They're not wrong. You'll get the marks for them, but in case there's a bigger margin for error in case you say something wrong. But stationary phase, mobile phase, and affinity, perfectly fine to mention them as long as you use them in the right way. But yeah, so if it's more polar, it means it has a higher affinity to the stationary phase, so it's more attracted to the stationary phase, and therefore it's less likely to break away. It'll be more strongly attracted to and bonded to the stationary phase, and it's less likely to move higher up. It's more likely to stay closer to the starting line. Whereas an apolar substance, or a non-polar compound, has a higher affinity to mobile phase than it does to the stationary phase, and therefore, because we're using an organic solvent here, which organic solvents are non-polar, so therefore since it has a higher affinity for the mobile phase, it'll find itself higher up to the stationary phase, because it has a high affinity for the mobile phase but low affinity for the stationary phase. It's always one or the other. So therefore, because of that, it will move much higher up the stationary phase, because it's more attracted to that mobile phase, and it'll keep going with it as much as the solvent heads will keep on going, and you'll find itself non-polar compounds will find itself higher up here. And I've got an example for that here. So separation and identification. So TLC plates can be used to separate and identify substances in mixtures. So here I've got an example of is that right? Yes. Here I've just got a quick example of a TLC plate for different amino acids, right? I have glycine, isoleucine, and phenylalanine. So you can tell here, I actually know the structure of glycine. Glycine's R group only has one hydrogen. You should know that as well. I mean, there's not, you don't have to remember all of them, but out of memory, I know that glycine has a, glycine's R group is just one hydrogen. Remember, the basic structure of an amino acid is the same. Obviously, you have your amine group, your carbon, amine group, carboxyl group, hydrogen, and R group. And it's the R groups that determine, this is how they determine what amino acids that you have. I know there's other methods like NMR, but in a chemical way of testing it, is chromatography. Is it a chemical way? No, I guess it technically would be a physical way of showing it. It's not, yeah, I guess it's more of a physical way of showing it, but it's an easy way of doing it, a very easy way of doing it. It doesn't require as much expertise in understanding it. You will need to understand NMR though, and there is a topic that I'll be going through very soon. But we understand what the basic structure of an amino acid is. Now, the R groups, you know, the only thing that's different between amino acids is the R groups. So this, that's not really relevant. It's only the R group that's really going to be able to determine what type of amino acid that you have. Now, glycine, it has the most basic R group out of all of them, and it's hydrogen. So it's a very non-polar compound. The carbon-hydrogen bond is very non-polar, and therefore it'll have a high affinity for the stationary, higher affinity for the mobile phase than it does with the stationary phase, and it will move higher up the stationary phase because it has a higher affinity to the mobile phase and a low affinity for the high affinity for the mobile phase and a low affinity for the stationary phase. Isoleucine has a bit of a longer R group. I think it's just like a propyl group, if I'm not mistaken. I think it might be a little bit of a chained propyl group as its R group, but it's slightly I believe that's slightly less polar. In case I'm wrong, double check that one, but I believe it's slightly more chained. And it's slightly more polar. It's slightly more polar. So if it's because it's slightly more polar, it'll have um it'll have a weaker affinity for the mobile phase compared to glycine. Not drastically like this, but just because I can give you a better example. But it'll have a weaker affinity for the mobile phase and slightly higher affinity for the stationary phase. So it won't move as higher up as it won't move as high up the chromatography paper. One compound that I do know for certain is very polar, is phenylalanine, and that has a benzene ring in it, and I believe, and that is more has more polar property, so I don't believe. Yes, yeah, benzene has to be polar. That electron dense ring in it and the way it behaves is definitely more polar, and therefore because of that it will have a higher affinity for the stationary phase, and you'll have a lower affinity for the mobile phase, and therefore it won't move that far up the chromatography paper. Now, I'm just giving you a couple of examples. You don't need to know these off by heart. I'm not trying to show you, but what you need to understand is that polar compounds have a higher affinity for the stationary phase and a low affinity for the mobile phase, so they won't move as far up, and it's vice versa, the opposite way around. So if it's less polar, have a higher affinity for mobile phase, low affinity for the stationary phase, and they will move higher up the chromatography paper. Now, I've said that enough times now, so I'm not going to mention it any more than I have to say it. That's plenty of times, so you get my point. I don't want to get you guys sick of me just constantly saying it all the time, or maybe you already have. I don't blame you. But the one thing I do want to make it clear is that it's from the highest point. So when you're trying to work out the RF values and how far it's moved up from the starting line, you do it from the high. I know they say something's going from the center, but really, if you're talking about how far it was able to get, it's really from how the tipping point. Now, tipping point can be kind of difficult to see, so I guess if you can't go to the main tipping point, you'd go to where it's most dense, the highest point of its density. So if it's kind of like, what I mean by that is, right, if you kind of got, imagine like a flame. You see like how when you're looking at your cocoa flame, it kind of looks like this, or that's, no, it really does not look like that. It looks more like this. Again, Doesn't look like that. That. And then so when you're looking at a cooker flame, it kind of looks like having like this really high part here, hot part here. Or if it's like a rocket ship, right? It has like this really hot, kind of. It looks like the flame is distorted into two parts. It's really a hot part here, and it's really hot part, less hot part here. Now, if you can't tell easily where the tipping point is here, I'd go for this point here. Now it's not the dead center. Dead center will be here. Now I go for here because that's more or less where its tip is. I mean, how fast it has, at least it's very easy to say it's at least got that far. The majority of them have got that far. That's where I would go for it. If it's more clear and it's more clear to see that it's a solid line that got to here, then go for that. But try and go for as high as you possibly can. That's visible and easy to see. Now the examiners have a range when you're going for your RF values. So if you've gone for something that's slightly more here than here, it'll be fine because the RF values would the RF values are going to be they'll be within a range. So if you get within that range, you'll get the marks. Now, luckily, don't have to worry too much about this if this makes you scared. They will try and make it as close as being this, or at worst, they'll make it this. And if they've given you this, then you can go for the dead center. Go for the dead center. If they've given you something like that, go for the dead center. They won't make it too crazy like this. But what I'm saying, if you're doing a practical, it may look more like this than this, and just kind of follow that kind of method towards it. That's how I do it, at least. But separation. So when separation is required, substances from the mixture can be isolated by cutting up regions with just one spot from the TLC plate. RF value. So we use RF values to identify substances. These values are calculated as first of all, that is how we'd go about measuring them. So we got the whole. First, we need to know the starting how far the solvent head has moved from the starting line, and here we measure that to be 13.9 centimeters. And if you wanted to do that, if you wanted to do work out how far our individual spots have gone, we go from here. As I've used a tip here, so 2.9 centimeters here, 7.4 centimeters here, and 12.8 centimeters. Now, how do we work out the RF value? Now, you guys know you should know how to work out the RF value by now if you've done basic GCSE, as I guess, but maybe some of you don't, and I'm gonna be fair on that. So the RF value is just a simple ratio of the distance traveled by the substance. So over simple division, distance traveled by the substance over the distance traveled by the solvent. Still going? We're still going. Okay, I thought it went off there for a second. And that is literally all you need to. That is the equation. So it's just to be the distance traveled by. Let's say you want to go for red here, right? For phenylalanine, the RF for phenylalanine would be 2.9 over 13.9. Don't times by 100. It's not a percentage. It will be a decimal less than 1, and that's how you should work out. So we can calculate the RF value for reference substances and the tested substance. So identification. So RF values depend on the solvent that they are measured in. The identification process is comparing the RF value of the reference and the tested substance. So first of all, how far these compounds would go depends on, as I said before, the organic solvent that you're using. If you're using a different organic solvent, phenylalanine could be less. It could be 1.9. Your isoleucine could be 7.1. My point being here is that your organic solvent really determines how far your compounds are going to move up the stationary phase. So when you're looking at, and all on top of that, you need to look at a reference, and the reference is just a book. So it's like all the RF values for all the different compounds. So because you need to understand what that mean, right? So if you have a compound, if you get an RF value of, let's say, 0.84, that doesn't mean anything if you don't have a reference. A reference is just literally, the reference that you understand will be, now, again, they'll tell you they'll give you the reference. It's just a book telling you the different RF values for different compounds. So say an RF of 0.84 is glycine, for example. And just saying, okay, I've done my experiment now, and I've got an RF value of 0.82, and it has the RF values for a specific organic solvent as well. So because different organic solvents will give you different RFs. So if a book says that the RF value for a specific organic solvent for glycine is 0.84, and you've done your experiment and your values are roughly 0.84, that's a match. You say that's okay, that matches with what the book says, therefore I know the compound that I have is glycine because I've got an RF value of roughly 0.84, and the book says an RF value of this particular type of organic solvent for glycine is 0.84. Okay, that's a match. Therefore, I know I have. Therefore, that is how you determine whether or not you have glycine. It seems very simple, I know, but I'm just trying to make it very obvious what I'm trying to say here. Yes, so the identification process is comparing the RF value of the reference and the tested substance. You need to have your reference, otherwise you don't know. You find that your RF is 0.84, but it doesn't really mean anything. What does that mean? You know, that's why it's important to compare that to your reference. In case they ever ask you, say, in case they ever ask for the whole process, obviously I said before now, I've gone through the whole process of set up, run the experiment, evaluating your results, being able to understand the separation and identification. But when you're saying that last part of identification, you have to mention reference, otherwise your points really mean nothing. So calculation for RF. So we have a mixture and we suspect that it contains a particular component, for example, propanol. Since the RF value are relative to the conditions, we must only compare values measured under the same conditions. So the best way to do this is to add a spot of the suspected component, for example, propanol, to the same TLC plate as the mixture and run them together. Then we can see if the RF values align. If the RF values do align, there's a significant evidence that the suspected component is in the mixture. Basically, what this is just saying here is that if you wanted to find out, for example, if you wanted to know if a compound is so if we have to make sure that both, for examples, are under the same conditions, right? So the best way to do this is add to a spot of the suspected components, for example, propanol, to the same TLC plate mixture and run them together. Alright, so we have the same solvent, and we wanted to know whether or not we have a compound of propanol, right? Now, if we have a suspected compound and we think it's propanol, one way of referencing is getting another TLC plate and adding a known spot of propanol. And if we run both TLC plates at the exact same time and we get both results, we know that they're both propanol because they've given me the exact same results under the exact same organic solvent and the exact same TLC plate and exactly the same conditions. So that's one way of doing it. The other way is just using a reference book to show you, but you can just do two examples at the same time. So one of our unknown compound and one of a known compound. If they give you the exact same value, you know that that both compounds are exactly the same. Alright, so uses of TLC. How some of the uses of TLC. Identification. Identification, which is RF values. And then separation. And that's just cutting regions of the TLC plate. So colorless chemicals. So some chemicals used in TLC can't be identified because they aren't visible on TLC plate. The following methods are methods for locating these colorless chemicals. So when you've done this, sometimes it's not always going to be colored. So it might be more difficult to you to actually see how far our compounds have gone up the TLC plate. So we need to think of a way we can actually identify it. So some chemicals used in TLC plate, TLC can't be identified because they aren't visible on the TLC plate. And following our methods, we're locating these colorless chemicals. So for example, we can add iodine, and iodine turns the color spots purple. And this is another method that allows us to see where the spots of the colorless chemical is, so that we can calculate the RF values. And another way we do it, we can actually add a fluorescent dye. And fluorescent dyes are visible when UV light is shone on them. And this allows us to see where the spot of the colorless chemical is, and so we can calculate its RF value. So I'm going to show you an example. So obviously, hopefully this made sense. So one way we can have when you basically what it will appear like, right, is that you have your TLC plate and it will look blank. You'll see obviously your solvent heads move up a certain way, so it can be kind of damp up until a certain point. But in terms of your points, you can't see them. It looks blank, like a blank piece of, well, obviously it's not paper. You know it's not paper, but it will look like a blank sheet. It's only when you've added iodine it will turn certain spots purple, and then you'll be able to see the spot here, spot here, spot here, and then you'll be able to work out your RF values. Or another way of doing it is you can add a fluorescent dye, and once you add a fluorescent dye, you'd then expose your TLC plate to UV light, and then the UV light will be able to show you where the spots are. It'll make it more like, they'll still be colorless, but they'll be more clear to see where those spots are. And yeah, so I'm going to show you an example seeing a TLC plate technique in practice, so hopefully this works. No technical difficulties. It's fine now, but I've got the video now, so hopefully this will give you a better understanding. The capillary tubes I have here, or this person has here really, they're what you use to so fusion tube, have it there. Capillary tubes. You use the capillary tubes to kind of dot your so once you've grounded down your sample, the way you actually dot your compound or your sample onto the starting line is with these capillary tubes. That's how you do it. So he's using his fusion tube as a way to actually store the compound. Also, I should say the compound, the sample, and then he's using the capillary tube. He puts the capillary tube into the fusion tube that has the sample in it to allow the sample to go into the capillary tube by capillaration. And then he uses the capillary tube to dot it onto the starting line. Now this is one method. See, this is how a chamber is meant to be. And I said there's slight problems with doing it this way. Now your organic solvent could go up the side of the container if it kind of like condenses, and you don't really want that. You don't really want it to kind of like some of your, if you have organic solvent that evaporates and condenses against the side of the container here, that could be a slight problem. So I prefer to suspend it. But this is one method that you could do. Chamber, and it won't be wrong. It's not gonna be wrong. It's just reason why I don't really like doing it that way. But your chamber here, evaporating dish over it, and this is how your chromatography paper would, how a chromatography apparatus would look like. I'll just continue here. You allow it to go for a certain period of time. Once that time has elapsed, you then he's used UV light. So now the chromatography's actually happened. He's seen the wavefront reach a certain point. But as you can see here, it is a blank piece of paper that he takes out. So the actual solvent front has gone to here, but it's a blank piece of paper that you can see. Look, it looks like a blank piece of paper there. But once you put it under the UV light, you can see now there's single spots here, but you can see that there is single spots product indicate product is true. So here we go. So you've used, this is clearly a reference here. So it has one reference and one they use the reference of doing it on the same chromatography paper, which is fine, or same TLC plate here. Is this a TLC? It looks like a TLC plate. Yeah. So they've done the reference on the same chromatography paper, which is fine if you have space to do it. So he has a reference on here, which is the pure product, coming up to here. So it's a pure product here of a pure amount of unknown substance is here, and it's gone up by chromatography, showing as a pure substance because it's gone up to this level here. Because there's only one spot. If there's only one spot, it means you have a pure product. But how we know it's a match is that we had our unknown sample that's here, and it's gone up the chromatography paper, but it's gone up to the same level. It's not an exact thin line, so it means it has some impurities. That's what it really means. But generally, this is a more or less a pure compound. There's no other. This isn't a mixture. It's meant to be as close as possible to being a pure sample, and we have a match because they've gone to the same level. And that's what it means. So that's what I understand. If they told me to, I say this because if they ask you to interpret your data, we say that this is, you have a reference here, your unknown sample. They've gone up, they've gone up the same level, so you know it's a match, and if they're both pure substance because there's no other dots. There's only one. The only thing you can maybe highlight is that this is a slightly thicker dot compared to this one, so it means that this might be some slight impurities, but generally. This is a match for being the same product and pure. And that's it. And that's it. Now if I go back to my video here. So, experimental setup. So, we see the TLC plate in the beaker or the chromatography chamber in a low level of solvent at the bottom of the beaker. Samples are dotted along the bottom and move up the plate as the solvent rises or as the mobile phase rises. And affinity. So if we look close, we can see the orange trail moves the slowest. It has the highest affinity for the stationary phase. So in our example before, this is meant to be orange. It should be red. Sorry. As you can see here, our red dot here has the highest affinity for the stationary phase and the lowest affinity for the mobile phase, and therefore it's moved up the least. This shows here that it's polar. But yeah, this is not a pure sample because here we have 3 dots, so it's not a pure sample. We have 3 separate compounds within this one sample here. But that red dot just indicates that it has a low affinity for the mobile phase and a high affinity for the stationary phase because it hasn't moved up the highest. Now that's it for these videos. Hopefully this video was helpful. Check out my other videos if you find them useful. Tell me just give me feedback on one of these, if anything I can improve on. I know I stutter a lot. I have retainers, so that's why I can't really speak clearly. But hopefully you find these videos useful, and that's it.